Hello everyone, this is Professor He again. Nice to see you all. The topic of this task is about the state of a system. And now, let's talk about continuum first. Matter is made up of atoms that are widely spaced in the gas phase, yet it is very convenient to disregard the atomic nature of a substance and view it as a continuous, homogeneous matter with no holes, that is, a continuum. The continuum idealization allows us to treat properties as point functions and to assume the properties vary continually in space with no jump discontinuities. This idealization is valid as long as the size of the system we deal with is not enough relative to the space between the molecules. This is the case in practically all problems, except some specialized ones. The continuum idealization is implicit in many statements we make, such as the density of water in a glass is the same at any point. To have a sense of the distance involved at the molecular level, consider a container filled with oxygen and atmospheric conditions. See the figure. There are about 3 times 16th power to 10 molecules of oxygen in the tiny volume of 1 cubic millimeter at 1 atm pressure and 20 degrees centigrade. The continuum model is applicable as long as the characteristic length of the system is much larger than the mean free path of the molecules. At very high vacuums or very high elevations, the mean free path may become large. For example, it is about 0.1 meter for atmospheric air at an elevation of 100 kilometers. For such cases, the rarefied gas flow theory should be used, and the impact of individual molecules should be considered. In this case, we will limit our consideration to substances that can be modeled as a continuum. Let's look at the figures. Is there any difference for the two systems? Yes, the same amounts of substances with same temperature are in different volume. How to distinguish? We can call the substance is in the different state. The word state refers to the condition of a system as described by its properties. Since there are normally relations among the properties of a system, the state often can be specified by providing the values of a subset of the properties. All other properties can be determined in terms of this view. Consider a system not undergoing any change. At this point, all the properties can be measured or calculated throughout the entire system, which gives us a set of properties that completely describes the condition or the state of the system. At a given state, all the properties of a system have fixed values. If the value of even one property changes, the state will change to a different one. In the figure, a system is shown at two different states. Thermodynamics deals with equilibrium states. The word equilibrium implies a state of balance. In an equilibrium state, there are no unbalanced potentials within the system. A system in equilibrium experiences no changes when it is isolated from its surroundings. There are many types of equilibrium, and a system is not in thermodynamic equilibrium unless the conditions of all the relevant types of equilibrium are satisfied. For example, the higher pressure at the bottom layer is balanced by the extra weight it must carry, and therefore there is no imbalance of forces. The variation of pressure as a result of gravity in most thermodynamic systems is relatively small and usually disregarded. If a system involves two phases, it is in phase equilibrium when the mass of each phase reaches an equilibrium level and stays there. A system is in chemical equilibrium if its chemical composition does not change with time, that is, no chemical reaction occurs. A system is in thermal equilibrium if the temperature is the same throughout the entire system as shown in the figure. That is, the system involves no temperature differential, which is the driving force for heat flow. Mechanical equilibrium is related to pressure, and a system is in mechanical equilibrium if there is no change in pressure at any point of the system with time. However, the pressure may vary within the system with elevation as a result of gravitational effects. A system will not be in equilibrium unless all the relevant equilibrium criteria are satisfied. Okay, that's all for this task. Thank you very much, and see you next time.